We spent a while on solving systems in two variables, right?
Too long.
Quite a while. So now that we know how to do two variables decently well, hopefully, we're going to start looking at solving systems of equations in three variables. Okay, today we will not be able to finish these notes. So there's not going to be an assignment tonight. You're welcome. We're just going to start the notes. We'll finish them either Monday or Tuesday of next week. Okay? These problems can sometimes take a while. Just a heads up. We ready to get started? Okay. So you don't necessarily have to write all this. This is all in your book. This is straight from your textbook. So if you just want to pay attention and look at this while I read it to you, go for it. If you want to write it down, you can write it down. I do not know how to do that from here to the projector. I know. I'm sorry. A linear equation in three variables, x, y, and z, is an equation of the form ax plus by plus cz equals d, where a, b, and c are not all zero. So none of those values are zero. They can be any other number than zero, though. The following is an example of a system of three linear equations in three variables. So this group of three equations is just an example of a system of equations in three variables. Okay? A solution of such a system is an ordered triple. What was my solution to a system in two variables? Not an ordered triple, but an ordered pair. So we always found an x value, and we always found a y value, correct? You guys remember that from systems in two variables? We always wanted to find both values. Here we've got three values. We got an x value, a y value, and a z value. Because it's got three variables, I got to solve for all three variables. So the solution is what we call an ordered triple, x, y, z, whose coordinates make each equation true. So once again, the ordered triple makes all three equations true, just like our ordered pair made both of our equations true. Right? You guys remember that? My ordered pair of my system in two variables made both of my equations true. My ordered triple makes all three equations true. The graph of a linear equation in three variables is a plane in three-dimensional space. The graphs of three such equations that form a system are three planes whose intersection determines the number of solutions of the system, as shown in the diagrams on the next slide. So I'll show you what each solution kind of looks like. Yes?
So, would we still solve them the same? We just have another variable to find?
Essentially, yes. So there's a few more steps involved than just the two variables. But we're still using the same processes we used before. Does that make sense? Same processes as in two variables, there's just a little more steps. Okay? So, hopefully this next slide's not too small either. Hopefully you can kind of see it. Once again, these pictures are in your book though. If my system of equations in three variables has exactly one solution, then this is kind of what it looks like. Here's one of my planes right here, this green plane. The blue plane is another one of my equations, and the red plane is one of my equations. They all meet at exactly 1 point. So that would be my one solution, x, y, z. Here's what it would look like if there was infinitely many solutions. Because these planes go on forever and ever and ever. They would be intersecting at this line right here, which this line goes on forever and ever and ever. So that would be infinitely many solutions. No solution is where the three planes do not have points in common at all. Two of my planes can have points in common, but they all three need to have points in common for it to be a solution. So here, not all three have a point in common. Here, not all three have a point in common. Here, none of them have any points in common. They're all parallel to each other. Okay? I'm not going to ask you to graph these or draw any graphs of these. I just wanted to show you what it would kind of look like if we were to graph them. Okay? So don't worry about graphing. Are there any questions so far? Okay. So here's some steps that we can kind of take to solve a three-variable system. Step one, we want to rewrite the linear system in three variables as a linear system in two variables by using the substitution or elimination method. So my very first step, I'm trying to simplify things for myself. I'm trying to take it from a system in three variables down to a system in two variables using some of my techniques I've already used. Step two, once I get it as a system in two variables, I want to go ahead and solve that new linear system for both of the variables that are left. So if I get it to a system that has the variables x and z in it, I want to solve for x and z first. Has everyone got that? Are we paying attention? Some of us are not paying attention. Some of us has our heads up or heads down. Some of our eyes are closed. So go ahead and get your heads up for me. Go ahead and get your heads up for me. Keep your eyes open, paying attention. After I do step two, after I solve the new linear system for both of its variables, I can then move on to step three, substitute the values found in step two into one of my original equations, like we've done in the past, and solve for the remaining variable. So if I've solved for x and z, I'd plug x and z into an original problem and solve for y. Everyone got it? When you obtain a false equation, such as 0 equals 1, just like in the past, we get no solution. You guys remember that? My variables cancel each other completely out. I had a false statement. I got no solution. Same thing applies here. When I do not obtain a false equation, if the variables cancel each other out, and I get an identity such as 0 equals 0, then the system has infinitely many solutions, also just like in the past. So if your variables cancel each other out, I get a true statement, I get infinitely many solutions. You guys remember that from two variables? For the most part, hopefully. This means yes.
Yeah.
This means no.
For sure.
This means I don't know what you're thinking. Okay? If y'all could participate a little bit, that'd be great. So are there any questions about any of my steps I'm going through right here? Are we ready to look at some examples? Perfect. Here's our first example. I would probably write this one down and write down all the steps we go through as we solve it. So here's my system, 4x plus 2y plus 3z equals 12. 2x minus 3y plus 5z equals negative 7. 6x minus y plus 4z equals negative 3. This is a system of equations in three variables. I've got to solve for all three variables. So what did step one tell me to do on my previous slide? Did anyone write down the steps or no? What does step one tell me to do on this slide?
Rewrite the linear system.
Rewrite my linear system in three variables as a linear system in two variables. So I want to condense this from three variables to two variables using some methods I've already used in the past. I would only really use substitution if you already have one of your equations solved for a variable. Are any of my equations solved for x or y or z?
The third one.
It's solved for x or y or z?
Well, why?
Y is by itself on one side of the equation?
No.
It is not. Are any of them solved for any variables?
No.
They are not. So I'm going to use elimination here. So I'm going to pick two of my equations to use elimination with, and then I'm going to pick another two to use elimination to get two equations and two variables. So, what looks like it's probably going to be the easiest to eliminate? Which variable?
X.
Which one probably has the smaller numbers?
Why?
Y. Y's got the smallest numbers, doesn't it? So I'm going to try to eliminate my y's. So what I'm going to do is I'm going to use my first equation and my third equation. So I'm going to rewrite those down here. My first equation and my third equation. And now I'm trying to eliminate the y's from these two equations. So what would I have to do to one or both of my equations to be able to eliminate my y? Multiply the second one now by 2. Does everyone see that? That way I get the same number in front of my variable. Right? So what's 2 times 6x?
12x.
12x. 2 times negative y.
Negative 2.
Negative 2y. 2 times 4z.
8z.
8z. And then 2 times negative 3. Negative 6. In these two new equations, this top one and this third one, do my y's now have the same number in front of them?
Yes.
Yes. Okay, do they have the same sign or different signs?
Different.
Different, so do I add or subtract them? Add them. So I'm adding this top equation with this bottom equation. Right?
Yeah.
So what's 4x plus 12x?
16x.
16x. My y's are eliminated. What's 3z plus 8z? 11z. And then what is 12 plus negative 6?
Positive 6.
Positive 6. There's one of my new equations that I'm going to be using. I have one equation and two variables. How many equations do I need in two variables?
2.
I need 2. So I got to kind of use the same process again using two different equations now. So I used my top one and my bottom one. Which two equations could I use now?
The bottom one and top one.
Well, I used the bottom and the top already.
Middle
Middle and top.
and bottom.
The middle and the bottom, right? So 2x minus 3y plus 5z equals negative 7. 6x minus y plus 4z equals negative 3. Now I'm trying to eliminate y again. So that way I get two equations that have the two same variables. Right? Up here I have x and z. So I want to eliminate y, so I have another equation with x and z in it. So what do I need to do to one or both of these equations? I want the same number in front of my y variable.
Times 3 on the first one?
On the first one,
Wait, no.
multiply my bottom one by 3. That way I can get 3 in front of y.
Oh, we're solving y.
Does everyone see that? 3 times 6x.
18.
18x. 3 times negative y.
Negative 3.
Negative 3y. 3 times 4z.
12z.
12z. 3 times negative 3.
Negative.
Negative 9. So now, I'm looking at this top equation and this bottom equation. I've got the same number in front of my y variable, correct?
Yeah.
Do I have same or opposite signs?
Same.
Same, so do I add or subtract here?
Subtract.
Subtract. So I have 2x minus 18x. What does that give me?
Negative 16.
Negative 16x. My y's cancel out. Now I have 5z minus 12z. What does that give me? Negative 7z. And now I have negative 7 minus negative 9. What does that give me?
2.
Positive 2. Does everyone see that? I am now done with step 1. That was only step 1. Fantastic, right?
Oh my god.
This is so much fun. You guys having fun yet?
No. Oh.
Okay, that's step 1. I rewrote my linear system in 3 variables as a linear system in 2 variables by using elimination. What does step 2 tell me to do?
Solve the new linear system for both of its variables.
Now I'm solving my new linear system right here in the upper right for x and z. Solving for those 2 variables. So this is just like what we were dealing with for the past week and a half, 2 weeks. Just solving this for x or z, or actually both of them. What method is going to be easiest to solve this new system of equations? Elimination or substitution? Elimination. What am I eliminating here? X. They already have the same number, correct? Do they have same signs or opposite signs?
Same, like no opposite.
Opposite signs, so do I add or subtract?
No, you add.
Add them. Because 16x plus negative 16x would cancel them out. 11z plus 11z plus negative 7z.
4.
4z. 6 plus 2?
8.
8. Is everyone kind of following along so far? It's going to help the more examples we do. I realize this is our first example though. But is it kind of making a little bit of sense as of right now?
Yes.
Hopefully a little bit. How do I get z by itself?
Divide by 4 on both sides.
Divide by 4 on both sides. So what does z equal?
2.
2. All right, I found one of my 3 variables. Sweet. 1/3 of the way there.
One equation is going to take a whole page.
But how do I find x now?
You plug it back in. For
Plug what back in where?
Z.
I got all these equations
Plug
lying
two in
around.
For Z. And use the middle one. Right.
What do you mean middle one?
Oh my god. Hannah, you do it then.
No, I'm not.
I'm going to be using one of these 2 equations, correct? Because I have z, I'm trying to solve for x now.
Yeah.
So which one do you want to use, top or bottom?
Either one.
It doesn't matter which one though. Pick one.
The top one.
Top one.
Yeah.
So we're plugging into the top equation.
This is over.
16x plus 11 times 2 equals 6. What's 11 times 2?
22.
22. Now I'm just solving for x. How do I do that?
Minus 22 on both sides.
That's what?
22 on both sides.
Minus 22 on both sides. 16x equals, what's 6 minus 22?
Negative 16.
Negative 16. Am I moving too fast for anyone? I can slow down if I need to. And how do I get x by itself now?
Divide by 16 on both
Divide by
sides.
16 on both sides.
Negative 1.
So what does x equal?
Negative 1.
All right, I found 2 of my 3 variables. We're almost there. That's the end of step 2.
Are you serious?
That's the end of step 2. I solved my new linear system for both of its variables.
You got 2 minutes.
Step 3, I now have to substitute the values found in step 2 into one of my original equations. So one of my 3 original. To solve for my remaining variable. To solve for y. Okay? We'll stop there today. We'll pick this up on Monday. We'll finish solving this system of equations. Any questions before I end the recording?
No.
Okay.